All right, hi folks, this is Larry Mussolino. I'm recording a video for Section 3.1. Chapter 3 introduces rules for differentiating. So what we'd like to be able to do is take a function and find its derivative function. And we mentioned last section, derivative function is going to give you the slope of the tangent line to the function at a certain point. What it really is going to provide is information about the rate of change. How quickly is the function changing? Maybe it's increasing very quickly, maybe it's decreasing very slowly, and so on. We'd like to understand about this rate of change. All right, so a little bit about notation. Remember, we're going to be using f of x to indicate the original function, and then typically we'll be writing f prime of x to mean the derivative function. Instead of f of x, we sometimes might write y, and then we could also write y prime to mean the derivative function. Okay, so this Section 3.1 is about different rules we're going to be using to find derivatives. You might remember in the last section, in Chapter 2, we talked about finding derivatives using a limit process. And that was somewhat tedious and time-consuming. You might remember we took the limit. So last section, we said if you want to know the derivative function, we take the limit as h approaches 0 of this fraction. And remember, this is really a slope calculation. It was y2 minus y1 over x2 minus x1. But we like to have a shortcut way to find the derivative functions so we don't have to take the limit whenever we need a derivative. So here are going to be some important rules that we'll talk about, and there'll be more rules we'll cover later on. All right, first one says, what's the derivative of a constant? The derivative of just a constant is 0. Let me give you a quick example. And by the way, we'll sometimes be using this d dx operator. d dx means take the derivative of a constant. This might be, for example, the derivative of, let's say, the number 17. Well, the derivative of any constant is equal to 0. I'll show you why that makes sense in just a second. Here's another rule called the power rule. Power rule is the rule we're probably going to be using the most often. It says if you're taking the derivative of x to an exponent, what you do is you bring that exponent down in front as a multiplier and then subtract 1 from the exponent. Let's do a quick example. Again, that d dx is telling you to take the derivative. Let's take the derivative of, let's say, x to the 7. Well, what this rule is telling me is take that 7 and bring it down in front as a multiplier and then subtract 1 from the exponent, so I end up with x to the 6. The next rule says if you're taking the derivative of a constant times a function, you can actually bring the constant out in front and then just take the derivative of a function. That's useful because sometimes this makes the derivatives simpler to work with. You take the constant and pull it out in front. This last rule says if you have, let's say, a function f of x plus g of x and you want to take the derivative, you can actually take the derivative separately of f of x and the derivative separately of g of x. All right, so let's go ahead and do some examples to see how these rules might work. Okay, so let's talk a little about the first rule that said if you take the derivative of a constant, you end up with the answer 0. Does that make sense? Well, if I think about a function that's a constant function, let's say y equals 17. This is a constant function, y equals 17. Well, the graph of y equals 17 is a horizontal line. Remember, the graph of y equals any number is just a horizontal line. But what's the slope of a horizontal line? The slope is 0. You might remember that from algebra. So it makes sense the slope of the tangent line to this horizontal line, the slope of that is 0. Again, the slope of any horizontal line is always 0. So it makes sense that if you were to take the derivative of any constant, let's say 28, you would get 0. The derivative of pi squared is just a number, it's a constant, that derivative is 0. All right, let's go to this power rule. How about if we want to take the derivative of x squared? The way I would do that is bring the 2 down in front as a multiplier and then subtract 1 from the exponent, so I'm really ending up with 2 times x to the 1, which of course is just 2x. Okay, let's do a couple more examples of this derivative function, of this power rule. How about the derivative of just x to the 1? Well, if you think about it, the derivative of just x is really the derivative of x to the 1. Bring that 1 down in front as a multiplier, and then subtract 1 from the exponent. That's what the rule tells us to do. But x to the 0, any quantity to the 0, is just 1. So it turns out the derivative of x is just equal to 1. All right, let's do some WebAssign examples. All right, how about this first one? It says, what's the derivative of 320? Well, remember, anytime you take the derivative of any constant, the answer is 0. So this answer is 0. How about the derivative of x to the 6? Well, the rule is bring that 6 down in front as a multiplier. So I'm going to write 6x, and remember you subtract 1 from the exponent, so the answer here is 6x to the 5th. How about if we were taking the derivative of 5x to the 3rd? Well, here's where I can use that rule that says you're allowed to take a constant out in front. So this constant 5, if I want to, I can bring out in front. So here it is, pulled out in front of the derivative. Now I'm going to take the derivative of x to the 3rd. Well, the rule is bring the 3 down in front as a multiplier. Here it is. And then subtract 1 from the exponent. So that leaves me with x squared. Of course, I copied down the 5 that I started with. And 5 times 3 is 15. So the final answer here is 15x squared for this one. Do a couple more WebAssign examples. Now, this power rule applies no matter what the exponent is. The exponent could be a negative number. The exponent could be a fraction. The exponent could be a decimal. This rule would still apply. So here's an example, x to the 0.7. All right, if I want to find the derivative, I'm going to take that 0.7 and put it down in front as a multiplier. So that's going to be 0.7x. Now I have to subtract 1 from the exponent. But 0.7 subtract 1 is negative 0.3. So the exponent here is negative 0.3. I could leave the answer like that, but sometimes you might want to write an answer with positive exponents only. You might remember if you have x to the negative exponent, you can rewrite it as 1 over x to the positive exponent. I'll give you an example. How about x to the negative 10, let's say? I could rewrite that as 1 over x to the positive 10. So in our example, if I wanted to get rid of the negative exponent, I could write this as 0.7. And I'm going to move that x to the negative 0.3 down to the denominator, which would be x to the positive 0.3. All right, let's do this bottom example. I want to take the derivative of this function, negative 6x to the 7. Well, I can really think of this negative 6 as a constant. So let me bring that out in front. And now let me take the derivative of x to the 7. Well, I'm going to bring the 7 down in front as a multiplier and subtract 1 from the exponent, so that makes it x to the 6. Now to clean this up, I'll just multiply the negative 6 times the 7, that's negative 42. So the answer here is negative 42 x to the 6. Okay, let's do a couple more WebAssign examples here. All right, a couple of these examples are going to involve square root functions. Well, you know, what I'd like to do is use that power rule. In order to use the power rule, I really need to have x being raised to an exponent. So you may remember that when you see a square root function like the square root of x, you can rewrite that as x to the 1/2. So I can always take the square root and rewrite it using a fractional exponent like this 1/2. So let me do that. I'm going to change this to be 7 x to the 1/2. Now let me take the derivative. Well, this 7 is just a constant in front, so I'm just going to bring that with me. Now let me take the derivative of x to the 1/2. The power rule says bring the 1/2 down in front as a multiplier, and then subtract 1 from the exponent. So that's going to be 1/2 subtract 1. But 1/2 subtract 1 turns out to be negative 1/2. So what I'm left with is 7/2 x to the negative 1/2. Could leave the answer like that. And if I wanted to get rid of negative exponents, I could also write this as 7/2 times x to the positive 1/2. Web assign should either take this answer or that answer. Web assign is pretty flexible on accepting different answers like that. All right, let's do one more example that involves a square root. I'm going to this bottom example. It's 20 over the square root of u. All right, again, I want to get rid of square roots and change to fractional exponents. So the way I'm going to write this is first change the square root of u to be u to the 1/2. But what I'd also like to do is move this u to the 1/2 up to the numerator. And I want to make this look like the power rule. So what I'm going to do is, if I want to move an expression up to the top, move from the denominator to the numerator, I could do that by flipping the sign on the exponent. So I could rewrite this as 20u to the negative 1/2. All right, now I'm going to take the derivative. Well, for the derivative function, I'm just going to copy down that 20 because that's a constant in front. So I'm just going to bring that with me. Now the power rule says take that exponent and bring it down as a multiplier. So I'm going to bring the 1/2 down with me and then subtract 1 from the exponent. So that's going to be negative 1/2 subtract 1. All right, let me just clean this up. 20 times negative 1/2, that's negative 10. And then 1/2 subtract 1 is negative 3/2. So I end up with negative 10 times u to the negative 3/2. And if I wanted to get rid of the negative exponents, I could move that u to the negative 3/2 down to the bottom. So it'd be negative 10 over u to the positive 3/2. Okay, so again, on these examples, you can see whenever you have a square root or even a cube root, you can change those to expressions involving fractional exponents. So remember, when you have a square root, you can rewrite that as x to the 1/2. If you have a cube root, say the cube root of x, you can write that as x to the 1/3. You might remember this from algebra on rewriting using fractional exponents. All right. Let's go to that one other rule that we were talking about. It says if you're taking the derivative of the sum of two functions, if you'd like, you can break it up and take the derivative of each function separately. So let's take a look at an example here. I'll take the derivative of this messy function here. Well, I can really think of this as like f of x, this is g of x, this is h of x, and so on. So I can really think of it as taking the derivative separately of each one of these. So I'm going to take the derivative of 4x to the 5 separately, derivative of 3x to the 4 separately, and so on. Now, sometimes you might not write it out like that just to save a little bit of time. But really what you're going to end up doing here is taking the derivative separately of each one of these 4 terms. So let's do it. How about the derivative of 4x to the 5? Well, I'm going to leave the 4 in front because that's a constant. Then I'm going to bring the 5 down with me. The 5 comes down in front for the power rule. and subtract 1 from the exponent. But 4 times 5 is 20, so that gives us 20x to the 4. All right, let's take the derivative of 3x to the 4. I'm going to bring the 3 with me because that's a constant in front. The 4, the exponent 4 comes down as a multiplier, and then I'm going to subtract 1 from the exponent, so that's x to the 3. But 3 times 4 is 12, so that's how I'm getting that 12x to the 3rd. Okay, let me move to the next one. How about the derivative of 8x squared? Well, for that, I'm going to bring the 8 down because that's just a constant in front. Take the derivative of x squared. The 2 comes down in front as a multiplier. Subtract 1 from the exponent. So I end up with 16 minus 16. All right. How about the derivative of just x? Well, you might remember the derivative of x is just 1. And how about the derivative of 3? Well, remember the derivative of a constant is 0. So we ended up really taking the derivative separately of each one of these expressions. All right, let's do one last WebAssign example here. All right, I'm going to let you do number 11, but basically you're just going to take the derivative of each one of these terms separately. So you'll take the derivative of negative x to the 3rd, then take the derivative of 7x squared, then take the derivative here of minus 8. Remember, the derivative of the constant is 0, so when I take the derivative of that 8 there, that's, of course, just going to be a 0. Let me go to the bottom example. The bottom example is a little trickier. Before taking the derivative, I'm going to do a little algebra to simplify things. Actually divide the numerator by the denominator. What I'm allowed to do is break this up into 3 separate fractions. So I can write this as 9x to the, I'm going to take each part of the numerator and put it separately over the denominator of x. So that's going to give me 9x to the 3rd over x minus 7x squared over x plus 5 over x. Now I'm going to simplify each one of these separately, then I'll take the derivative. So f of x now is going to be 9x squared minus 7x plus 5. Now I really have an x to the 1 on the bottom of this fraction, but I'm going to move that x to the 1 upstairs into the numerator, and that's going to flip it to be x to the minus 1. All right, now we could take the derivative, because now each one of these expressions looks like the power rule can be used. So let me take the derivative of each one of these. The 9 is a constant, so I'm just going to copy that down. I'm going to take the derivative of x squared. Bring the 2 down in front as a multiplier and subtract 1 from the exponent. So that leaves me with x minus 7, and the derivative of x is 1. And then we take the derivative of x to the negative 1. I'm going to bring the negative 1 down in front as a multiplier and then subtract 1 from the exponent. But negative 1 subtract 1 is a negative 2. All right, let me write the final answer. Maybe I'll write it up here, the final answer. Then I can write it as 18x subtract 7 minus 5, and I'm going to put the x squared on the bottom to flip it to be a positive exponent. Okay, so this is the derivative function. And you might say, well, what's the point of the derivative function? Remember, we're trying to find the slope of the tangent line at a specific x value. In fact, let's do an example to illustrate that. Okay. Do problem 15, because problem 15 is a little different. Let me help you with problem 14, just with the setup. So I'm going to rewrite this. Notice it says move the expressions on the bottom to the numerator using negative exponents. So what I could do here is write this as f of t equals, I'm going to write it over here, maybe easier. F of t, So the t to the fifth is in the denominator, move it up to the numerator, and that's going to flip it to be t to the negative 5. Minus 3 t to the negative 3 plus 2 t to the negative 1. Now I'm going to let you take the derivative of this function, and of course you'll take the derivative separately for each one of these three expressions. All right, let's go down to number 15. Number 15 says find the slope and then find the equation of the tangent line to the function at the given point. All right, well, here's what we're going to do. First, we're going to find the slope of the tangent line. Well, the derivative function gives you exactly that. The derivative function gives you the slope of the tangent line. So let me go ahead and find the derivative function using the rules we've just talked about. So I'm going to write here f prime of x equals, all right, negative 3/2 is a constant, so I'm just copying that down. I'm bringing the 2 down. Remember, I'm taking the derivative now, x squared, and that leaves me an x plus 8 times the derivative of x, but that's just 1. Then when I take the derivative of this constant 8, it's just 0, so I don't need that. All right, so it looks like the derivative function then is going to be negative 3x. This 2 cancels out with that 2. Negative 3x plus 8. What this derivative function gives me is the slope of the tangent line for any x value. So if you give me an x value, I'll plug it in the derivative function, and that will yield or produce the slope of the tangent line at that x value. Well, I'm noticing here that they're asking us to use the x value of negative 1. So what that means is I want to find this derivative function when x is negative 1. So that's going to be negative 3 times negative 1 plus 8. But that's positive 3 plus 8, so it's 11. But that 11 is the slope of the tangent line. So just to give you a quick example, imagine this graph did something like this. And here's x equal negative 1, let's say. Here, let me try to draw the tangent line to that graph at that point. What we just figured out is the slope of this blue tangent line is 11. So the slope is 11. But now they want us to go one more step and actually find the equation of that blue line. Of course, that's a straight line, so we can use this formula, y minus y1 equals m times x minus x1. Here's the x1 they gave us, and here's the y1 they gave us. We know m is 11, so let's go ahead and plug in. So it's going to be y minus a negative 3/2. But when I subtract a negative like that, it's going to flip to be y plus 3/2 equals m. Our m is 11, x minus x1. Our x1 is negative 1, so that's going to be x minus a negative 1, but that's going to be x plus 1. Let me multiply the 11 inside the parentheses. So that's going to be y plus 3/2 equals 11x plus 11. And to finish, I just want to get y by itself. So let me go ahead and subtract 3/2 from both sides of this equation. So I'm going to subtract 3/2 from both sides of this equation. When I do that, it looks like I'm going to end up with y equals 11x. Now I know 11 is the same as 22 over 2. I want to get the same denominator. So now I need 22 over 2, subtract 3 over 2. Again, the only reason I changed 11 to 22 over 2 is to get the same denominator so I can subtract these two quantities. 22 subtract 3 is 19, so that looks like 19/2. So this is the equation of the tangent. All right, folks, hope this is helpful as you're working in Section 3.1, finding derivatives.